Welcome to calculus.
After many years of combining like terms to make one expression, now we get to take it all apart.
On this episode, Stevenson will demonstrate
Let's talk about a topic that we haven't seen in a while. Let's talk about local linearity. Remember, the idea of local linearity is that every curve, when you zoom in on that curve, it starts to look like a line, right? Okay, so let's extend on that a little bit. Suppose I have my nice radical function here, the square root function, and I want to focus on the point 1, 1. There it is. Now, I want to look at the tangent line on that point. There it is. Now we can see the tangent line, right, touches the curve at exactly one point. That's why it's called a tangent line. And we understand that at each respective point on the domain of the square root function here, will each have its own unique tangent line. But there's an idea that we can use this tangent line to actually approximate the values of the curve, as long as you're really close to this point. Let's look at this a little bit. If I zoom in here, you can see the tangent line at this point and around it almost looks identical to the curve itself. But the farther away I get from this point, notice there's separation. This tangent line isn't the best in terms of approximating, but when you go farther away from your point, but notice right around this point, it is a very good approximation. And if I continue to zoom in, you'll see, even if I get into smaller values here, I'm still really close to that curve. So what we can do is linearize or create a linear function, which is essentially just the equation of the tangent line. And we can use that to actually approximate the output values of the original function. But we have to be careful because the approximation isn't as good the farther away from our point as we want it to. And we can see that visually by those spaces. The other thing is that how is it going to be an approximation? Is it going to be an over approximation? Could it be an under approximation? Well, using the graph here, we can see that if I come up with any approximations on this tangent line, since the tangent line is above my curve, that means these approximations I get will be slightly over the actual value. If my tangent line was below my curve, then my tangent would be, or my approximations using my tangent line would actually be a little bit under or an underestimate. So let's look at how we actually create this equation. The good news is it's not really anything new. It's stuff we've already been doing. So let's remember, what do we need in order to write the equation of any line we want? We need a point and a slope, right? So typically x1, y1 is the format we use for our point, and the slope at the particular x value we call m. So how do we write the equation of a line? Well, we use point slope form, as you see there. And we can modify this into slope intercept form. It looks something kind of like that. So notice all I did was move the y1 term to the other side. Okay, so this is something we're used to. Now this is if you're using the secant line though. Remember, we're trying to use the tangent line to do our linearization, or in other words, our approximation of our original function. So if we need to find the equation of the tangent line at a specific point, how does our previous formula change? Well, our point is a particular x value, and so it's just a f of a. F of a just represents what is the output at a. But notice the slope we're calling f prime, because remember, the derivative represents the slope of the tangent line. Okay, so that's important to remember that concept. The derivative is used to find the slope of the tangent line. Regular slope formula is used to find the slope of the secant line, which is average rate of change. So how does our equation change? Well, this is point slope form. Remember, it was the previous form, but now instead of there being a y1 or an m or an x1, we have f of a, f prime of a, and x minus a. So the formula is still structured exactly the same. The main difference here is you're using a particular ordered pair, which we get, but the main difference is that we're using the derivative of our slope. And sometimes it can be modified into slope intercept form, and it would look like the following form in green. So this is what you essentially copy down in your book. See? f of a plus f prime of a times the quantity of x minus a. So whenever you're asked to linearize or approximate a given function, you're going to be using essentially the equation of the tangent line. So this is what I mean earlier when I said we've already been doing this. That's pretty awesome. This is nothing new. We're just now using the equation of the tangent line in order to make approximations.